In this video, we're going to be talking about the Pythagorean theorem and how we can use it to find a missing side in a right triangle. First thing we need to understand is what are the pieces of a right triangle called? So the longest piece, or this diagonal length, is always called the hypotenuse. It's always the longest side, and it's always the side that's across from the right angle. Remember that the longest side is always across from the biggest angle, and in a right triangle, these are both acute angles, smaller than this right angle. So the right angle is the biggest one. So across from that will always be the longest side. So the hypotenuse is always the longest side. That means that we have two shorter sides. We call those legs. It doesn't matter which one you call leg 1 or leg 2. You have your choice. If we take those lengths and just give them variables, we're going to give them lowercase letters. And so the side length lowercase letter is always going to be across from the uppercase letter for the angle. So the angles are all uppercase letters. C is most typically that right angle. And across from it would be side length lowercase c. Across from angle A would be side A with a lowercase letter, and across from angle B would be side B with a lowercase letter. So that's the typical way to describe a right triangle. If we can identify the hypotenuse and the legs, then we can start to use the Pythagorean theorem. Pythagorean theorem can be defined a lot of different ways. Let's define it using words. We can say that the sum of the squares of each leg is equal to the square of the hypotenuse. That doesn't make much sense. Let's try and look at it using some symbols. So if I take my leg value and I square it, I take my other leg value and I square it, then that represents the sum of our legs squared. And then on the other side of the equal sign, we have our hypotenuse squared. So the hypotenuse squared is equal to the sum of the squares of the two legs. And then if we once more just use our symbols here, taking those letters that we used to describe the side lengths over here, a squared plus b squared equals c squared. What we can do from there is actually solve for each of these pieces of the right triangle. So if I want to solve for the hypotenuse, or c, I just square root both sides. So c equals the square root of the sum of those squares of the legs there. So we could say it in words or we could say it in symbols. Take your pick, whichever one you like best. If I want to solve for one of the legs, a squared for instance, I could subtract b squared, move it over to the other side. So now I have c squared minus b squared. And then to undo that a squared, I square root both sides. So a is equal to the square root of the difference between the two squares here, the hypotenuse squared minus the leg squared. If I want to solve for the other leg, or b, I would just switch the a and b letters, and we get our other third formula here. So we can use the Pythagorean theorem to solve for each of the pieces of a right triangle, but we have to know two of the pieces, 2 out of the 3 sides, in order to do it. Let's do some examples. So in this triangle, let's identify what pieces we have. We have a leg here value and a leg value here, and we're missing the hypotenuse. So I'm going to say my leg, or 3 squared, plus my other leg squared, or 4 squared, is equal to my hypotenuse squared. We could simplify first. 3 squared is 9, 4 squared is 16. I could add those together first, and then solve for c by square rooting both sides, undoing that square by square rooting. And so we get our value for c, or the length of the hypotenuse, is 5. This is known as a special right triangle because it's in the side length ratio 3, 4, 5. And that ratio will always be true if you double it, triple it, cut it in half, whatever you want to do, that ratio will always be true. So if you can recognize those special right triangles, then you may not have to do the Pythagorean theorem. You could just state your value and give your reason you know it's a special right triangle. Let's do another example here. This time we're missing a leg value, or leg length. So I'm going to say 12 squared plus b squared is equal to 13 squared. And so we could do the same process we did over here. We could simplify first, then move things around. But I'm going to show you how to do it another way. Let's move things first before we simplify. So if I move that 12 squared over to the other side, then I have 13 squared minus 12 squared. And then if I want to solve for b, I have to undo that square by square rooting both sides. And so b is equal to the square root of the quantity 13 squared minus 12 squared. Check it out. That's what we said one of our equations for the leg was, right here. So the more you get familiar with using the Pythagorean theorem, maybe the more comfortable you are with just jumping straight to one of those equations rather than having to set it up first and then moving. So we can actually skip these previous steps and hopefully just start right here. So now we can simplify. 13 squared is 169. 12 squared is 144. 169 minus 144 is 25. And the square root of 25 is 5. This is also a special right triangle. It's in the side length ratio 5, 12, 13. And again, any scale of that ratio is also true. You could double it, triple it, cut it in half. Doesn't matter. That ratio will always be true for this special right triangle. So those last two examples were nice rational answers, but we can actually use the Pythagorean theorem with some irrational values. And we'll just do the same process. Identify your hypotenuse. That needs to go by itself on one side of the equation. These are my two legs, so I'm going to square all of these values. And once again, we could simplify first and then move stuff around and solve. But once again, I'm just going to show you more tricks that we can do. If I move or subtract 5 times the square root of 7 squared to the other side, and then square root both sides to solve for x, then we're trying to simplify this. And we can actually do this all in our heads. So 5 squared is 25. The square root of 13 squared is 13. So this value is 25 times 13. But I'm just going to leave it like that for a second. Do the same thing over here. Squaring 5 gets me 25, and squaring the square root of 7 gives me 7. So this quantity is 25 times 7. Now let's just work on factoring, because that'll help us reduce the size of our numbers. Since both of these terms have a 25 as a factor, I can actually factor that out of both of these and write my leftovers inside the parentheses. So I factored out of 25, and that left behind 13 minus 7. I can take the square root of 25 out. That's a 5 at the front. And simplify 13 minus 7 and be left with 6 under the radical, which we can't simplify. So we're able to find the solution without multiplying these numbers, getting really big numbers and doing our work with those. Sometimes we can use factoring to simplify our work. Just another different method that we can use. One of the cool things about the Pythagorean theorem is that we can use it to find the diagonal length in a square or a rectangle, because we can actually break those shapes up into two right triangles. So in this example, we're going to find the diagonal length of the square by using the Pythagorean theorem. So because my two legs are both 5, then I'm going to say 5 squared plus 5 squared equals c squared. Just set up the Pythagorean theorem. We can start to simplify. 5 squared and 5 squared is 25. And then if I square root both sides, then I'm trying to simplify the square root of the sum of 25 plus 25. But again, we could factor. So because both of these terms have a 25 in them, I could factor that out. And that leaves behind a 1 plus a 1. And I could take out the square root of 25, which leaves a 5 at the front. And then leave behind that 1 plus 1, which gave us 2 under the radical. So just another way that we can simplify our Pythagorean theorem. This also is a special right triangle. So anytime we break up a square into two right triangles, we actually create a special right triangle based on angle measurements. So this is a special 45, 45, 90. And the shortcut that we'll learn a little bit later on is that it's the leg times the square root of 2. That's always the diagonal. And also there's a special 30, 60, 90, which again is another special right triangle that we'll dive into a little bit later. We can prove that these ratios are true by using the Pythagorean theorem. But again, we'll work on this one in a few videos from now.